So how do I make a representation for a relation? It's one thing for me to write a list of ordered pairs, for me to make a table, for me to make a little arrow diagram, but I'm not sure those are computationally useful. So there are several varieties of available changes we can make. There's a matrix and a graph. So let's start with a relational matrix. I am going to assume to start with that we are working on the relations on a set A. What does it mean to be a relation on A? Exactly, I'm going from A to A. In that case, I'm going to list the elements of A in some order. And then I'm going to define an array, a matrix. And I'm going to talk about the entries double subscripts, where I is the row and J is the column. And what I'm going to define is that the IJ entry of M is either a 1 or a 0. It's a 1 if AI is related to AJ. It's a 0 otherwise. All right. We did an example on Monday. We looked at the set A being the numbers 1, 2, 3, and 4. And we used the relation A is related to B was defined as A divides B. You already have a listing of what divides what in this set. Go find it. There are 4 elements in my set, therefore I'm going to have 4 rows and 4 columns. The first row goes with the first element, so does 1 divide 1? Does 1 divide 2? Does 1 divide 3? 1 divides 4. 2. Does 2 divide 1? Does 2 divide 2? Does 2 divide 3? 2 divide 4. 3. 3 divide 1? 3 divide 2? 3 divide 3? 3 divide 4? 4. What's this row? Ta-da! If I am doing a relation from A to B, then A defines the rows, B defines the columns. The same idea still applies. Now that means if you change the ordering of the elements, you are going to change the matrix involved. So I had the very first relation, I think I had the numbers 1, 2, 3, and 4, and then I had A, B, C, and D, right? Those have clearly, I hope, an order that you would expect them to be in. There's no requirement. I could put these orders in these elements in any order I want. And that means that this matrix is not unique, because we could rearrange the elements. Same game. Now we have two different sets. Set A is the numbers 1 through 3. Set B is just the numbers 1 and 2. And A is related to B if A is strictly greater than B. What should this matrix look like? How big should it be? Ian? Okay, but the order in which I give those numbers matter. I'm always going to describe a matrix rows, then columns. So is it 2 rows, 3 columns? Or is it 3 rows, 2 columns? Use the AIs for the rows, the Bs for the columns. So how many should I have? Right. I should have a row for 1 and 2 and 3 and a column for 1 and 2. We're not required to put these sorts of outside markers on them, but until you get used to keeping the order of which place in which, yeah. Again, I think I mentioned this last time. Whenever I talk about a matrix, I talk about it in row column fashion. Two-dimensional arrays are defined RC. Hey, Seton Hill's a Roman Catholic institution. There you go. Okay. Some of these entries are zeros. Some of these entries are ones. Which ones are which? Seth.
The first row I got no, no. Second one I got yes, no. And the third one, yes, yes.
Ta-da. Two is bigger than 1. 3 is bigger than 1. 3 is bigger than 2. Wherever I see that relationship hold, I'm going to put a 1. You were using yes and no. You could use trues and falses. I'm thinking a matrix of numbers. I could think of it as a matrix of Boolean entries. It's still the same idea. When I am dealing with a relation from one set to another, sometimes it pays to label the outside of the matrix like this. Those of you that go on to take graph theory, math 342, will see a lot of places where we use this exact idea. Matter of fact, we'll use it a little bit later today. When we're dealing with a relation between two sets, labeling this way is usually helpful, but it's not required. Questions? If I have a matrix, I can deduce the relation from it. I have not labeled the outside, so this is a matrix on the relation. So we're going from the set A to the set A. I just decided to call the set A ABC. Call it anything you want. 1, 2, 3, red, green, blue, doesn't matter. What's related to what?
AC and CA are both false.
And everything else?
It's true.
So A is related to A is related to B, but A is not related to C. B is related to A, B is related to B, B is related to C. C is not related to A, but C is related to B, and C is related to C. Hey, wait a second. We had a bunch of properties for relations on Monday. I listed 4 properties. What were those 4 properties? But wait, there's more. Antisymmetric. I would like to know which of those properties apply here that I can determine fairly easily. Some of these properties are easier to determine than others. Is this relation reflexive? Brent, why?
Because A is related to A, B is related to B, and C is related to C.
So every element is related to itself. But even if I didn't have this list, I could tell from the matrix, couldn't I? This long diagonal here, going from upper left to lower right, is referred to as the main diagonal of a matrix. If every element on the main diagonal is a 1, then my relation is reflexive. Emily, I'm using that IFF as if and only if again. So my matrix, my relation is reflexive if and only if the main diagonal is always a 1. If any of those numbers are a 0, that would tell me, hey, this element isn't related to itself. We're not reflexive. Because reflexive means it's a universal statement, 1 counterexample, and we're out. How about symmetry? Is this relation that we've described here symmetric? Emily, how do you know?
Because A is relational to B and B is relational to A, and then when you don't have it, like A is not relational to C and C is not relational to A.
And if I reverse the letters, even if the letters are the same, the relation is still there, right? So I can see from here that this relation is symmetric. How can I see here?
If you put it over the main diagonal, you fix it the same.
A matrix is symmetric if when I change the row number and the column number, I get the same thing. M is symmetric if Mij is the same as Mji. Reversing the row number and the column number. So if I take this row and compare it to that first column, those are exactly the same. If I take the second row and compare it to the second column, the third row and compare it to the third column. This idea of switching rows and columns is usually called the transpose of a matrix. And for those of you who've done any Excel work, when you copy and paste a set of values, you can transpose them. So what was a giant row now becomes a giant column of numbers. That's the actual definition of this transpose idea. Our relation is symmetric if and only if its corresponding matrix is symmetric. Huh. Reflection seems easy. Symmetric seems easy. Anti-symmetric. What does it mean for a relation to be anti-symmetric again? Emily?
If A is relationship with B and B is the relationship of A, then A is equal to B for all of A and B.
All right. That sounds effed up. If A is related to B and B is related to A, then they're the same thing. If I'm dealing with where A and B are the same, that's the diagonal, right? So I really only care about what's going on away from the diagonal. Like I did with being symmetric, I want to look at the entries that are not on the diagonal. So let me think about this. I'm going to suppose for a moment that I have a set of size 3, A, B, and C. If this relation is anti-symmetric, and I have a 1 here, what does that mean?
It should be a row.
Opposite side how? Because then I would have, this says B is related to A. But here I have A is not related to B. If both of those were a 1, then A and B would have to be the same thing. And A and B are clearly different things because I put that in the 1, 2 and the 2, 1 spot, right? Second row, first column, first row, second column. I can only have one of those be true at a time. Right? Could both of them be 0? If both of them were false, then that false arrow true, wouldn't I? So I need A related to B but not B related to A. Or I need it the other way around. I need one of those to be a 1 and one of those to be a 0. How do I get one of them to be a 1 and one of, I can't have them both be 1s. Right? Can't have them both be 1s. But if they were both 0, then I would have A related to B and B related to A, arrow A equals B. I need that. If one of those is false, what's the statement inside the parentheses? And false arrow, anything is true, right? I need this sentence to be false. In order for this sentence to be false, what's the negation of this sentence? Oh, crap. I got to go back to chapter 1. What's the negation of this sentence?
A is not related to B, or B is not related to A.
That's the negation of this part. What's the negation of the whole thing? I'm going all the way back to page 27, chapter 1, section 2. You wrote this down on your first formula sheet for exam 1. Go find it. It starts with, I think so. P arrow Q. The negation of that is not P and
No, yes, right?
I didn't. When in doubt, let's go look at page 27. I apologize. It's not page 27. It's page 29. I even circled it. P and not Q, right? So A is related to B and B is related to A. And A and B are different. So if I had 2 1s on the diagonal, sorry, off the diagonal in symmetric spots, that means that it is not antisymmetric. If I have 2 zeros, it's fine. If I have 1 0 and 1 1, it's fine. The only thing that's a problem is when I have 2 1s off the diagonal. If I have 1 1 and 1 0, I'm fine. If I have both zeros, I'm fine. The only way I break antisymmetry is when I have something that's symmetric. But it only has to be symmetric once. It doesn't have to be symmetric everywhere. It only has to be symmetric once. That's a little less obvious, isn't it? There's a lot more comparison going on. I don't like it as much. Our relation was symmetric. It can't be anti-symmetric. We'll do some more examples. Transitive is hard from the matrix. In order to make transitive easier, I need to define some operations on matrices. I'm actually going to define two new relations. Hang on a second. Let's suppose I have relation 1 and I have relation 2. And they're both on the same set. Well, then each of those has a matrix, right? But R1 and R2 are subsets. And if they're subsets, then I can define other subsets, right? We had R1 union R2. We had R1 intersect R2. But how did I know when you were in the union? One or the other. That's an or. I'm going to define an operation on matrices. The symbol I'm using is the or symbol. I don't know why the people who did this didn't decide to call this or. I would have called this or, but some schmuck decided to call this the join of two matrices. I hate this term. This comes from the language of filters, but how did I know if I was in the intersection? I love it when they're playing out in the field, really, honestly, I do. What was that, Emily? Exactly. So I'm going to define the and of my two matrices. Again, I didn't define the term. We're going to call that the meet. It's just and, it's just or. And you do this one entry at a time. Matrix 1 ij or matrix 2 ij. 1 or 1 is 1, right? 1 or 0. We're going to do Boolean arithmetic, just like it was trues and falses. And I replace this with an and to do the meet. So if I give you two matrices, we should be able to, from these, compute the meet and the join. What is the join? Come in. One and one, 0 and 0. Sorry, or. 1 or 1. 1 or 0 is a 1. 0 or 1 is a 1. 0 or 1 is, I'm just doing the or all the way across each row and each column. Do an and across each row and column. What do you get? I should have a lot fewer ones this time. Exactly. In a way, I think of the or like adding. And I think of the and like multiplying. Because when I do 1 times 1, I get 1. But if either of them are a 0, 1 times 0 or 0 times 0 is a 0. So I think of the and like multiplication. I think of the or like adding. Only then I'm saying 1 plus 1 is 1. Kind of. It's a very weird addition, but it's an addition. Back in chapter 2, I skipped a section. Chapter 2, section 6. Chapter 2, section 6 happens to be all about matrices. And there are some other types of operations on matrices. There's something called the Boolean product. This is on page 182. The Boolean product allows you to multiply a matrix by another matrix. Any of you done any matrix multiplication in any other course ever? Okay, I got a couple of yeses and a couple of nos. The way you multiply a matrix is to go across one row, the row on the left matrix, across the row and down the column at the same time. The symbol for a Boolean product is a dot inside a circle. I have a matrix A and another matrix B. When I do the product, the thing that goes in this first spot goes across the row and down the column. If this is the 1, 1 spot, we use the first row and the first column. To do the 2, 1 spot, you go the second row with the first column. But I multiply the first number by the first number. I multiply the second number by the second number. The third number by the third number, all the way across the row, all the way down the column. That's a whole bunch of multiplications. And then I add. Multiplying and adding. So in order to do this, I do AB, IJ. I take the ith row of A. And I go one at a time across that row. I take the jth column of B. That means I need to go through each of the rows. I got to multiply those. Which was multiplying? And or. Or. Something times 0 is always 0. There are more zeros in the or. And then I have to AND these. K equals 1 to however many there are. That's disgusting, isn't it? Let me write that again. And K equals 1 to N, A, I, K, or B, K, J. You ready for the sick part? You can multiply a matrix by itself. If I do this with a single matrix, I can define the matrix A squared as A Boolean product A. I'm pretty sure you're already looking at me like I'm the sickest mother on the face of the planet. But here's the best part. You can figure out whether or not your relation is transitive by looking at the square of the matrix. There are direct computational packages for doing Boolean matrices. Am I going to make you do this crap by hand? Hell no. Should you know how to do it? Yeah. Computation is not long when the matrices are small. The matrices are larger. This is a pain in the ass. And I default to doing this by technology. So it is possible to figure out from a matrix whether or not a given relation is transitive. It is not trivial. We'll do more of this in the linear algebra class for those of you that have to take that. Something called the matrix exponential that works with this quite a bit. We had relation 1 and relation 2 up there, right? So if I want to do the matrix for relation 1 composed with relation 2 composition, then I do the matrix for relation 1 Boolean product, the matrix for relation 2. Let me go back and show you how that works for this first setup. This was our relation 1 and relation 2 matrix, yes? So I'm going to go across this row and down this column. One, 0, 1. Or those together, I get a 1. 0, 0, 0. What do I get? A 0. See? I got to go across and down. It's not a short process. With a larger matrix, I'm in deep trouble doing this by hand. Trust me, there's easy code defined to do this online. Don't do it by hand. I don't want you to. But I actually find transitivity easier to do with pictures. So let's talk about the other way of representing a relation. Now, when I say the word graph, most of you will think of something we did back in algebra class or in Calc 1, right? I got a function, I draw a pretty picture. But we defined a graph back in chapter 2, section 4. A graph was the set of points x, y that made our thing true, right? But now I don't actually have a true statement, a false statement the same way. So what I'm going to do is I'm going to define a digraph. This is short for directed graph. I'm going to define this by saying I have a bunch of dots. We'll call them nodes or vertices. A is a set of dots, nodes, vertices. We're going to label them. Labeled like whatever the elements of A are. Let's say I'm using the numbers 1, 2, 3. I'll label my dots 1, 2, 3. I'm using the set ABC. I'll label them ABC. I'm using your names. I'll label them all with you. Doesn't matter. I just have to label these items. I'm going to draw an arrow from item I, AI, to AJ if AI is related to AJ. Think about this in terms of the matrices. I'm going to draw an arrow wherever there's a 1 in my matrix. An example. A is the set of numbers 1, 2, 3. My relation is A is less than B. Here are my 3 nodes, the vertices of my digraph. Where do I draw the arrows? Seth?
1 to 2, 1 points to 3, the 2 points to 3.
And that's it. I only draw an arrow from A to one item to another if the first item is less than the second. I could give you a random relation. I've given you the nodes. That's the set A. I've given you the set of arrows. That's the set R. I can think of each ordered pair as a source and a destination, an arc that goes from the first coordinate to the second coordinate. Make a picture that goes with this. I draw an arrow from 2 to itself. One goes to 3, 1 goes to 4, 2 goes to 1, 2 goes to 2. 2 goes to 3. I drew that so I wouldn't have to draw one arrow over another, but you don't have to do that. You can cross them up. I don't care. I'm just being a pain in the ass here. 2 goes to 3. 3 goes to 1. 3 goes to 3. 4 goes to 1. And 4 goes to 3. I will call an arrow that goes from a node to itself, I'll call that a loop. A question for you. Is this relation reflexive? I got rid of the ordered pairs on purpose. So push them off the top of the screen, you can't see them. Blaze, you shook your head. Tell me why. And I know that from this because there's no loop there. A relation is reflexive if every node has a loop. Is this symmetric? Say that a little louder, Ian. I have one direction, I don't have its reverse. I do have 1 going to 3 and 3 going to 1. I have 1 going to 4 and 4 going to 1. I don't have any connection between 2 and 4. That's fine. I have this connection from 4 to 3. I don't have the reverse. I have this connection from 2 to 1. I don't have the reverse. Every time I have an arrow in one direction, I need to have its mirror image. Is this anti-symmetric? If A is related to B and B is related to A, then A and B are the same thing. Do you have any cases where A is related to B and B is related to A? Well, yeah, I have that right here, right? 1 goes to 3 and 3 goes back to 1, but 1 and 3 are different things. There would be a 1 in the matrix here. There would be a 1 in the matrix here, but those are different items. That's my broken case for antisymmetry. How do I know whether or not this is transitive? I need to look at any set of 3 dots, and I need to find a triangle. Like I can go from 1 to 3, I can go from 1 to 4, and go from 4 to 1. So 1 to 4, 4 to 3 works, right? So if I go from 1 to 4 and 4 to 3, I can go directly from 1 to 3. I can go from 3 to 1. I can go from 1 to 4. Can I go from 3 to 4? It's not transitive. I found a triangle that's not oriented with the arrows going in the right direction. So it's easier to check transitivity from a diagram, in my opinion.
If you had one triangle that had going back and forth and it was transitive to that triangle, did it matter that 2 isn't involved in that triangle at all?
No, I'm going to do just 1, 3, and 4. Then I'm going to do 2, 3, and 4. Then I'm going to do 1, 2, and 3. Then I'm going to do 1, 2, and 4. Every set of 3 has to work. It has to be transitive for all A, B, and C, right? So I have to be able to take any group of 3. That means I should be able to say 1 and 3 and 3. Can I make a triangle with just 1 and 3 and 3? Well, 1 and 3, I can go from 1 to 3. Technically, that's an oriented triangle. It's not actually a physical triangle, but it's an oriented triangle.
All of them need to climb on themselves for that to be impossible?
No. Because if it doesn't loop on itself, I can still work with that part, right? I just can't work to itself, right? I go from 3 to 1. Where's your next step? Not 1 to 1, but it could be 1 to 3. It could be 1 to 4, right? Let's figure out what are the outs from wherever I just landed. I think of this like a set of one-way roads. And what transitivity says is you don't ever have to take 2 steps, or if you can take 2 steps, you could also take 1. If you can go from this node to this node, and then to this node, you have to be able to go that way. That's what the orientation means for transitive. Before you run off, I said something backwards. I effed up. This statement, the ands and the ors are backwards. That definition appears on page 192. I apologize. I wrote the ands and the ors backwards. I said it one way correctly. I said it the other way incorrectly. This is the correct version. Definition 9, page 192. I will see you all. Have a wonderful rest of your day. If you came in late and have stuff for me, come give it to me.